begin with, we're going to talk about what the equation is going to look like. So many equations, right, will give you a rate of growth or decay. So when we get down to the example problems at the bottom, you're going to see they're going to give us some sort of percent. Usually it's a percent, or it might be something like half, something like that, where they're talking about how much is my situation growing by or decreasing by. So you can think about a situation, popular one in fun popular culture would be like zombies, right? Okay, so for every zombie that's created, he can then infect other zombies or create other zombies, right? And so they're growing at a rate of doubling, usually, some rate per day, okay? And so we're going to talk about with these equations, right? We can use kind of a formula where our y is equal to an a, and then a 1 plus or minus that rate that we're talking about to the x power, right? So these are all exponentials, which we know means that you have an x in the exponent, okay? Not a 2 or not a 4 or some number there, but an x in that exponent. And the a represents the starting value. So if we're talking about our zombies, right, and there's one zombie to start, right, then a would be 1, okay? Or if we're talking about money that's growing, let's say we're talking about $1,000, right? The starting amount of money would be $1,000, right? So that a number in front of the parenthesis would be 1,000, okay? And then the rate we have to represent as a decimal. So if we're talking about increasing by double, right? Or if we're talking about increasing by 5%, right? If we're talking about earning money, then we're talking about the percentage as a decimal. So 5%, for example, is not 5, right? The number 5 is not the actual number I want, right? When I try to turn a percent into a decimal, I have to think about dividing by cents. How many cents are in a dollar, right? So 5 divided by 100 will give me that rate as a decimal. So 5% is actually 0.05 as a number, right? And so we need to change that to a rate, right? Which is this. This is the percent, but this is the rate. And then the x is going to be the time. So if you have exponential growth, notice I wrote two things here. I wrote plus or minus. If you have an exponential growth, then you are going to do 1 plus your rate. But if you have an exponential decay in there, you're going to write 1 minus your rate, right? Clearly adding to 1, right? If I start from 1 and I add to it, right, I'm going to be increasing by that amount. If I start from the whole number 1, right, and I subtract from it, then I'm going to be decreasing by that amount. So let's talk about some key words that talk about growth and decay, because these are going to be important when you're looking into your problem. So what words represent growth when you're reading a word problem? Well, an easy one to identify and really often used is just the word increasing, right? If we're increasing by a certain amount, then we are, I'm going to do this in blue because that color is not quite bright enough, I think. Increasing, okay? And the opposite of that, right, if we're talking about decay, something going down, remember our growth is something that goes up and our decay is something that goes down. Well, the opposite word would be used, right? Decreasing. All right. And then we have a couple more words that might be less common, okay, but are still used, right? If we are growing, something like double might be common. And if we're decreasing, we might say half of something, or sometimes in science, we talk about something called a half-life. So things that are radioactive, right? They tend to sort of break down at a rate of a half-life, and we can calculate how long it takes for something to lose its sort of value as it breaks down into smaller pieces. So doubling or a half-life would be a decay. And then we also might hear the word, especially when we're talking about money or the value of something, is that it appreciates. Like if I buy a painting, right, over time, a lot of times that painting might go up in value as maybe how old the painting is. It would appreciate in value. But if we buy a car, for example, typically cars, as they get older, they depreciate in value, right? They go down. So I buy a car, and next year it's not worth as much, and next year it's not worth as much, because as I drive it, I kind of cause damage to it, or the value of it goes down. And so appreciate would be the growth one, depreciate would be the decay one. And a little bit easier word that means the same thing as appreciate and depreciate would be to gain value or to lose value. Okay, so these mean the same thing, but a lot of times you'll see this word because they're using more complicated vocabulary, right? They're using vocabulary that you should know as a high schooler. So appreciate and depreciate. All right, so as we go through an example, I'm going to show you how this is going to look. Here's example number 1, and it talks about in 1990s Florida, the population was 13 million, and the population was increasing at a rate of 1.7% each year. So I know I'm starting with 13 million and I'm increasing, and here's the amount I'm increasing by. Okay, and that happens each year. And then the population growth since 1990, right? That's my starting year is 1990. So how do I write this equation? Well, the starting amount is the population when I start in 1990. So 13 million is a big number, right? 13 million. What is that growth factor? Well, it's growing by 1.7%. But remember, we have to change percents to decimals. So when I divide this by 100, I'm going to get a number that is 0.017. And you can do that in your calculator, right? So 0.017 would be that decimal. And then the number of years since whatever that is, 1990 in this case. And so I take my year, if we're talking about today, right, then it would be 2024, right, minus 1990, which would give me 34 years, right? 34 years have passed since 1990. And so the number that is my x would be 34 in this case. So writing an equation, right, to figure out today's population in Florida would include y equals, right, the 13 million, that's the a value, 13 million. And then remember the formula says if you are increasing, what do you write? Okay, let me zoom out just a little bit so you can see a little bit better. The top part. We have the starting value, that's my a value. And then we have 1, and we're going to have plus or minus. Well, in this case, am I increasing or decreasing? Well, I'm increasing. So I'm going to write 1 and then plus my rate, which is 0.017. And then I'm going to write it to the x power. But in this case, x is representing 34 because that would be 34 years since 1990, right? So I would figure out and I would write 34 there. And that's how I would create the equation to solve this function. Okay, so this just has me write the function. I'm not even going to go ahead and solve it for this one. I just want you to write them out. All right, example 2 is very similar. I'm going to have you guys try that on your own. Example 3 is a little different, so I'll do that one for you. It says the half-life of iodine is 4 days. Half-life, okay, that's what I was talking about dividing something in half. A technician measures 40, millisomethings per whatever, a sample of iodine. Doesn't much matter what the amount is. It could be milliliters, whatever, right? And this is the name of the product, iodine 124. The 124 is not a number I actually need in the problem. Okay, that always throws students off. But it's called iodine 124, just like you have the color yellow number 5, right? When you talk about food dyes, that's just the name of the product. So how much iodine 124 is left in the sample after 4 days? All right, so the initial amount, how much did I start with? I started with 40, right, MCIs. Am I growing, right, or decaying? Well, it says half-life. Half-life means that I'm breaking it down by half every day, right? So half would be 1/2, which also would be 0.5. This is the decimal version of 1/2. I need the decimal version, right? Whenever I put this in, I said up here that we need to have the decimal. Okay, we need to have the decimal. We cannot put in, right, whatever we need unless we have that decimal. All right, so I'm going to flip over onto the other side and finish this because it's split onto 2 pages. The time it told me was 4 days. All right, so let's write the equation, and then here it does ask me to solve it. So my starting value was 40, right? Remember the equation is y equals a, and then 1 plus or minus the rate to the x power. Well, in this case, I'm going to do 1, always 1, and then am I doing plus or minus? If I'm doing a half-life, I'm cutting it in half each day. So I'm going to do minus, and then my rate from the previous page, right? My rate was 0.5. So I'm subtracting 0.5 from 1, and I'm doing it to the fourth power. Why fourth? Because x, right, x here is 4, okay? It says after 4 days. Well, if I do this in my calculator, I can do it mathematically right here. I can do 40 parentheses 1 minus 0.50, and then to the fourth power, right? That will give me the answer that I need. I can also actually figure out what 1 minus 0.5. This is the same thing as saying 0.5, right? Because 1 minus 0.50 actually equals 0.50, right? 1 minus a half is a half. And so I could also write it like this. Either way would give me the right answer. Notice if I put in 40 and then 0.50 and then to the fourth power, I should get the same answer of 2.5, right? So after 4 days, I only have 2.5 MCIs left. I started with 40, right? I started with 40. That was my A value from the front page. And my R value was this. And after 4 days, that's where I'm at. And think about it. If I started with 40 and I divided by 2, right, or I divided it in half on the first day, I would have 20. Then if I divided it in half again on the next day, I would have 10. And then again on the next day, I would have 5, right? So I've divided once, twice, 3 times. I need to do it one more time, right? Divide by 2 again, and I get 2.5. So you could do it 4 times, right, and get the answer. Or you can use the formula, right, which helps you to do things more quickly because you're just repeating that multiplication 4 times, or division, right, 4 times. In this case, you're kind of dividing because it's a decimal smaller than 1. Okay, so you guys have some practice problems to try out here. I'm going to let you guys try a bunch of these ones, okay, and try out writing them on your own. On the second page, there are also some problems here that I just want to quickly show you how to do. These ones are a little bit almost easier. They just give you the formula without the situation, all right? So here I have, right, the 1200 times 1 plus 0.3 to the t power. Does this represent exponential growth or decay? We'll see it has a plus here. And so if it's a plus, then it's a growth. What's my initial value? My initial value means my starting value. So in this case, my starting value is that A, right? And this is the 1 plus the rate to the t power, t being the time. So what's the rate of growth or rate of decay? In this case, the rate of growth is 0.3. What does that represent? In order to figure out what that percent was, I have to think about multiplying that by 100, right? If I do 0.3 multiplied by 100, my growth is 30%. All right, I'm going to look at a little harder one down here. All right, so this one, notice 100 times 1.25. They've actually put 1 plus 0.25 already together, right? So this represents this. So 100 is still my starting value, but looking at it, thinking about it's a number greater than 1, so I had to add something to it to get that, right? I had to add something to the 1 to get that 0.25. And so it must be, it's again asking, is it a growth or decay? It must be a growth. What's your initial value? 100, right? That's the starting value. That's your A value. And this is your rate, that 0.25, right? So 0.25 is your growth rate, but what does that represent? Again, we multiply it by 100, which means that represents 25%. Okay, so hopefully you're kind of seeing how these work. I'm going to do number 4 too, because this is the same sort of thing, but notice if I had to get a number less than 1, then I subtracted something from it, right? So this, I had to get that from 1 minus something, right? 1 minus something had to give me that 0.65. And in order to figure out what I subtracted, right, to get 0.65, I can take 1 and subtract 0.65, right, or 0.65. What if I do that? 0.65. I get 0.35, right? That's the number. That is my rate that I'm decreasing by, right? So 1 minus 0.35 had to be what I subtracted in order to give me that 0.65. So is it a growth or decay? Well, it's less than 1, so it has to be a decay. And what was my initial value? Still just the number in front, right? So 5,575. And if it's a rate of decay, I need to look at that number, right? I subtracted 0.35 each time. And if I think about that as a percent, that means it's 35%. All right. So hopefully